Hello everyone and welcome. Today we are diving into a topic that sits at the very core of modern AI, the training methodologies behind large language models. If you ever wondered how a raw neural network becomes a capable, helpful assistant like ChatGPT or Claude, the answer lies in a carefully orchestrated sequence of training techniques. Training an LLM is not a single step. It's a pipeline of distinct methodologies, each serving a specific purpose. We'll walk through the complete journey, the overall training pipeline and its stages, pre-training and self-supervised learning, supervised fine-tuning, reinforcement learning from human feedback, parameter efficient fine-tuning techniques, advanced and emerging technologies, and the practical considerations that lie it all together. Whether you are an aspiring AI engineer, a developer, or simply curious about these systems are built, this video will give you a clear, structured understanding. So let's get started. Before we go deep into each methodology, let's get the bigger picture. Training a modern LLM happens in distinct stages, each building on the last. Think of it as a progression. Pre training, the model learns language and world knowledge from massive amounts of raw text. This produces a base model, knowledgeable but not yet helpful or aligned. Supervised fine tuning, the base model is trained on curated examples of instructions and ideal responses, learning to behave like a helpful assistant. Preference alignment. Examples are RLHF, DPO. The model is refined using human preferences, learning to be helpful, honest, and harmless. A helpful way to think about it, pre training is like a person reading the entire internet, gaining vast knowledge but no sense of how to apply it in conversation. Supervised fine tuning is like an apprenticeship, learning by example how to respond appropriately. Preference alignment is like receiving ongoing mentorship and feedback, refining behavior to match what people actually want. Each stage uses a different methodology, different data, and different amount of compute. Retraining is by far the most expensive. The later stages are progressively cheaper but critically important for making the model useful. Now, let's examine each methodology in detail. Pre-training and self-supervised learning. The foundation of every LLM is pre-training, and the methodology that powers it is called self-supervised learning. Let's understand what makes it so powerful. Traditional supervised learning needs labeled data examples where human have marked the correct answer. That's expensive and limited. Self-supervised learning is different. The data labels itself. How? The model is given text and asked to predict part of it from the rest. The label is simply the next word, which is already in the text. No human annotation needed. This is what allows trainings on trillions of tokens because the internet provides essentially unlimited self labeled data. The dominant pre training methodologies for models like GPT is casual language modeling or next token prediction. The model sees a sequence of tokens, it predicts the next token, its prediction is compared to the actual next token. The error drives parameter updates. Because the model only looks at previous tokens to predict the next, it is called auto-regressive. This is ideal for text generation. Another pre-training methodology is masked language modeling, used by models like BERT. Here, random words in a sentence are hidden, masked, and the model predicts them using context from both directions, before and after. This is great for understanding tasks but less suited to generation. Modern generative LLMs predominantly use the autoregressive next token approach. The mechanics of training are during pre training, the core learning loop uses forward pass, that is, the model processes input and makes predictions, loss calculation. A function measures how wrong the predictions are. Backpropagation. The error is propagated backward to compute how each parameter contributed. Optimization. An optimizer, usually a variant of gradient like Adam, updates the parameters to reduce the loss. This repeats across countless batches of text over weeks or months. A few important concepts are batch size, how many text sequences are processed together before updating. Larger batches give more suitable updates. Learning rate, how big each parameter adjustment is. Too high and training diverges, too low and it's painfully slow. Schedules gradually adjust this overtraining. Epochs passes over the data. For massive LLMs, often just one pass or less because the dataset is so enormous. No single machine can train a huge LLM. Pretraining is distributed across thousands of GPUs or TPUs using techniques like data parallelism, model parallelism, and pipeline parallelism. Coordinating this efficiently is a massive engineering challenge and a big part of why training frontier models is so difficult and expensive. The output of all this is a base or foundation model. It's rich in knowledge but not yet a helpful assistant. Next level is supervised fine tuning. Once we have a base model, the next methodology is supervised fine tuning, often abbreviated as SFT. This is where the model learns to be helpful. The base model is trained purely to continue text. If you ask what is the capital of France, it might respond with more questions or continue as if writing a quiz because that statistically valid continuation does not inherently know it should answer you. SFT fixes this. Supervised fine tuning uses labeled examples, but now the labels are curated demonstrations of desired behavior. Each training example is typically an instruction or prompt, the ideal response. For example, prompt summarize the theory of relativity in 2 sentences. The response is a clear, correct 2 sentence summary. The model is trained on thousands to millions of these high quality pairs. It's the same underlying mechanism as pre training, predicting tokens, but now on examples that demos how a helpful assistant responds. When the training data spans a wide variety of tasks and instructions, this is called instruction training. It teaches the model to follow instructions it hasn't seen before. This is a big reason modern assistants can handle such diverse requests. In SFT, quality trumps quantity. A smaller set of excellent, diverse, carefully written examples often beat a huge set of mediocre ones. The model closely imitates the style, tone, and quality of these demos, so they must reflect exactly the behavior you want. Teams invest heavily in creating or curating these datasets, often using expert human writers. After SFT, we have a model that follows instructions and behaves like an assistant, but it still has limitations. It may not always know what humans prefer among several valid responses, and it may not reliably avoid harmful outputs. That is where the next methodology comes in. Next methodology is RLHF, reinforcement learning from human feedback. The methodology that truly transformed LLMs into a polished assistant is reinforcement learning from human feedback, or RLHF. This is one of the most important techniques in modern AI. Let's break down. SFT teaches the model to imitate good responses, but there are two problems. It's hard to write demos for every situation. It's often clear and easier for humans to compare two responses than to write the perfect one. RLHF leverages human preferences, judgments about which response is better, to refine the model beyond what demonstrations alone can achieve. It's a three-stage process. 1. Stage 1, collect preference data. The model generates multiple responses to various prompts. Human labelers then rank or compare them. Response A is better than response B. This creates a dataset capturing human preferences about helpfulness, safety, tone, and accuracy. Stage 2, train a reward model. Using this preference data, a separate model, the reward model is trained to predict how humans would rate any given response. Essentially, it learns to assign a score that reflects human preference. It becomes an automated stand in for human judgment, able to score millions of responses without human involvement. Stage 3, optimize the policy with reinforcement learning. Now, the LLM called the policy is fine tuned using reinforcement learning. The loop, the LLM generates a response, the reward model scores it, the reinforcement learning algorithm adjusts the LLM to produce higher scoring responses, and then this cycle is repeated. Common algo here is PPO, stands for proximal policy optimization, which updates the model carefully so it improves without drifting too far and breaking what it already knows. KL constraint, an important detail during RLHF. We don't want the model to change too drastically and lose its knowledge or start gaming the reward model. So, constraint based on something called KL divergence. It keeps the updated model close to the original SFT model. This balances improvement with stability. RLHF has pitfalls. One is reward hacking, where the model finds ways to score high on the reward model without genuinely being better, like being verbose, sycophantic, or exploiting quirks of the reward model. Managing this is an ongoing research and requires careful reward model design and monitoring. Despite challenges, RLHF is huge reason model become genuinely helpful, safe and aligned with what users want. It's the difference between a model that can respond and one that responds the way people actually prefer. Next, we'll go to parameter efficient fine tuning. Full fine tuning, updating all of a model's billions of parameters is expensive and resource intensive. This led to a family of methodologies called parameter efficient fine tuning or PEFT. These let you adapt models cheaply. The core idea is instead of updating every parameter, PEFT methods update only a small subset or add a small number of new parameters while keeping the original model frozen. This dramatically reduces compute and memory needs. The most popular PEFT method is LoRa, low rank adaptation. The insight is instead of modifying the huge weight directly, LoRa adds a small low rank matrices that capture the needed changes. Only these small matrices are trained. The benefits are remarkable. Train a fraction of the parameters, sometimes less than 1%, vastly reduced memory requirements. The original model stays untouched, so you can swap different LoRa adapters for different tasks. It's much cheaper and much faster than full fine tuning. An extension called QLoRa goes further by quantizing the base model, storing it in lower position to save memory, while still training LoRa adapters. This makes it possible to fine tune very large models even on single consumer GPU. It democratized fine tuning, putting it within reach of individuals and small teams. Next, we will go to the advanced and emerging methodologies. Finally, we will take a look at some advanced and emerging training methodologies shaping the cutting edge. One is DPO, direct preference optimization. We discussed RLHS complexity, collecting preferences, training a reward model, and running reinforcement learning. DPO, direct preference optimization or DPO, achieves similar alignment goals but more simply. It optimizes the model directly on preference data using a clever mathematical reformulation, skipping the separate reward model and RL loop entirely. It's more stable, easier to implement, and has become very popular as an RLHF alternative. Reasoning focused training. A major recent frontier is training models to reason better. Techniques train models to generate step by step reasoning, chains of thought before answering. Some approaches use reinforcement learning specifically to reward correct reasoning paths, dramatically improving performance on math, logic, and complex problem solving. This reasoning training is one of the hottest areas in the field. Continued pre-training and domain adaptation. Organization often takes a base model and continue pre-training it on domain specific data like medical, legal, or financial to specialize its knowledge before fine-tuning. This domain adaptation produces models expert in particular fields. These methodologies represent where the field is actively pushing forward. So let's bring it all together. We have journeyed through the complete LLM training pipeline. Pre-training via self-supervised learning, building foundational knowledge from massive text, supervisor fine-tuning, teaching the model to follow instructions and be helpful, RLHF, aligning the model to human preferences for helpfulness and safety, parameter efficient fine-tuning like LoRa and QLoRa, adapting models very cheaply. Emerging methods also we covered like DPO, reasoning training, and mixture of experts. Understanding these methodologies demystifies how modern AI is built. It's not magic, it's a thoughtful engineering pipeline combining scale, quality data, human feedback, and clever algorithms. And with techniques like LoRa and QLoRa, these capabilities are increasingly in reach for developers everywhere, not just big labs. So, thank you so much for watching. If you found this valuable, please give it a thumbs up. Subscribe for more AI and machine learning content. Until next time, keep learning and stay curious. Thank you.